Welcome back to the Ultimate Class 10 Boards Prep. Today, we are breaking down the laws of reflection and the behavior of spherical lenses. But before we fully load the core engine of this explainer, we really have to respect the raw stats of our main subject today. Light travels in straight, rectilinear paths at a completely insane speed of 3 × 10 to the power of 8 meters per second in a vacuum. That is a speed run literally no one is beating in our universe. If you drop a tiny opaque object in front of it, it casts a super sharp shadow, which proves it absolutely loves those straight lines. Section 1. Core System Rules, the Laws of Reflection. So these rules strictly dictate exactly how light bounces off highly polished surfaces. First law, the angle of incidence, which we'll just call I, is exactly equal to the angle of reflection, or R. Basically, if a laser hits a mirror at a 30-degree angle, it's going to bounce off at exactly 30 degrees. Second law, the incident ray, the normal at the point of incidence, and the reflected ray all lie in the exact same plane. And hey, these aren't just polite suggestions. They apply to absolutely all reflecting surfaces everywhere in the cosmos. Now let's contrast your standard everyday mirrors with the upgraded gear. Plain mirrors? They give you a basic, predictable rendering. The image is always virtual, erect, the exact same size as the object, and laterally inverted. Your left simply becomes your right. But spherical mirrors, oh man, that's where the physics engine gets a massive update. They offer these curved surfaces that create totally reality warping, magnified, or shrunken images, depending entirely on where you stand. Section 2. Lens Upload, the Flashbang Helix. Right, so when parallel rays of light pass through a convex lens, they converge at a single point, known as the principal focus. Imagine a converging lens as an instant blindness effect in a game. Those parallel light rays violently crash into one intensely bright focal point after refracting through the curved glass. It is essentially a +100 XP flashbang straight to the retinas. Okay. To put it calmly in the precise syllabus terms you need for your boards, the principal focus of a convex lens is the real point on the principal axis, where light rays parallel to the axis converge after refraction. Because a convex lens is physically thicker at its center and thinner at the edges, it naturally forces all those incoming parallel rays to bend inward, right toward that single powerful point. And we can rapidly contrast that blinding convergence with the concave lens. While the convex lens brings everything together to a real focus with a positive focal length, the concave lens is all about scattering light away. It's a diverging lens. It literally spreads the rays out, making them look like they're coming from a fake, virtual focus with a negative focal length. They are totally opposite playstyles. Section 3. Mirror Upload, the Infinite Void. Let's systematically look at the exact image formations as an object pushes closer and closer to a concave mirror. When the object is at infinity, the image is just a tiny point at the focus. Move it to the center of curvature, or C, and the image is exactly the same size. Push it between C and the focus, and boom, the image gets enlarged. And notice the nature here? It's always real and inverted, hanging upside down in front of the mirror. That is, until we cross a critical threshold. Now, if the object is placed between the focus and the pole of a concave mirror, the image formed is virtual, erect, and magnified. It appears behind the mirror. It's almost like an infinite Let's reboot that audio. Apologies for the system error. Formally, a virtual image is an image formed by the apparent intersection of light rays. It appears behind the mirror and cannot be captured on a physical screen. By placing the object ultra close, right in that forbidden zone between the focus and the pole, you completely break the pattern of real images. You create this magnified, upright illusion that's permanently trapped right behind the glass. Section 4. Inventory? Real-world loadouts. All right, here is your optimized player loadout derived straight from your NCERT solutions. You've got the concave mirror, which is your absolute primary tool for car headlights and torches. You've got the convex mirror, the undisputed best choice for rear-view vehicle mirrors. And of course, you've got the convex lens, your classic go-to magnifying glass. Let's break down the stats on these. Equip, concave mirror. Function, maximum beam throw. See, if you place a light bulb exactly at the principal focus of a concave mirror, the mirror catches all that diverging light and blasts it out as a super powerful, parallel beam straight ahead. That is exactly how car headlights cut right through the darkness on an empty highway at night. Next up, equip, convex mirror. Function, maximize field of view. Have you ever wondered why rearview mirrors in cars always say objects are closer than they appear? Well, it's because convex mirrors always produce diminished, erect, and virtual images. By making the image smaller, they grant drivers a massively expanded rear-view field of view, letting you spot a huge area of incoming traffic in just one tiny piece of curved glass. Pretty clever, right? Now, imagine a scenario where you're forced to read tiny, practically unreadable dictionary letters. To get the absolute ultimate magnification item for this, you want a convex lens. But what kind? You're going to want one with a short focal length, specifically 5. 5 centimeters, to be exact. The physics validates this strategy perfectly. Shorter focal length equals higher converging power. If you use a 5-centimeter convex lens and place that tiny dictionary print between the optical center and the focus, you're essentially forcing the lens to generate an intensely enlarged, easily readable virtual image. A lens with, say, a 50-centimeter focal length, it just wouldn't have the same bending power to get the job done. Section 5. Final boss check. Simulation complete. Ultimately, the strategic placement of objects against these curved surfaces entirely dictates the reality we see. Which leaves us staring into the digital void with one final question for you to ponder as you conquer the rest of your physics boards. If these simple lenses and mirrors can so easily bend, magnify, and warp every single thing we see, is anything we perceive actually real?